In this video, we're going to solve integrals using integration by parts. All right, so let's take a look at the first problem. Here we want to find the indefinite integral of x times cosine of 5x dx. And so what this means is find the antiderivative of x cosine 5x. All right, now as we go through these problems, you might be wondering, well, could we use a u substitution, let's say? However, for these videos, we're going to strictly try and solve the integral regardless of if it could be solved another way. In a later section, in later videos, we'll talk about just being given a general integral and how do you approach solving it? Which method do you choose? But for all of these problems, we're using integration by parts. Okay, so here's the formula for integration by parts. And over time, as you work more and more problems, you'll end up memorizing this formula. So it's the integral of u dv is equal to uv minus the integral of v du. Okay, the idea is this is the integral you're starting with. This integral of u dv is this. And so we're going to come to the integral and we're going to identify we're going to choose which portion of the integral is going to be the u and which portion is going to be the dv. And then once we've chosen that, we're going to write this out, uv minus the integral of v du. And the idea is if integration by parts works, then what you end up with is a simpler integral here than what you originally had. And so this integral you can solve. That's the general idea, but technically, maybe this integral you wind up with isn't simpler than the original integral, but the integration by parts still works because even though it's more complicated, you can solve it for some reason. Like there's a technique that now you can use with this to solve it. The idea is that the integral you get here is solvable. And in most cases, the reason it's solvable is because it's simpler. Okay, so the first step, though, is to come to the original integral, and you're going to need to choose which portion is going to be the u and which portion is going to be the dv. Now, one thing to note before we get into this problem, and I wish I would have made this clear in the previous video when we went through the textbook section, but so, okay, let's say you identify, u is, I'm just going to make something up here, x squared plus 1, okay? Well, all right, we know that. We can take du dx, and that's going to be equal to what? 2x, okay? And then, like we've talked about, we can operate with these du's and dx's as if they were differentials. So we can multiply both sides by dx and get du is equal to 2x dx. Okay? And so what I want to point out here is that when you've got like a du or a dv or a dx by itself like this, so like du equals something, dv equals something, dy equals something. In most cases, and I might even say in all cases, I can't think of when this wouldn't be the case, you're going to have, so you'll have du is equal to something, something, dx or d whatever, right? Because the idea is, where did this come from? You had like d dependent variable divided by d independent variable is equal to something, and then you multiplied both sides by the denominator to where you get, d independent variable is equal to some function d dependent variable is equal to some function d independent variable. And the reason I'm pointing this out is because when we identify what the dv is, we're going to call one portion of this is going to be u. U is not going to include dx. Like whenever you just have like u, like a variable is equal to something, there's not going to be any, and for the most part, I guess to me in all cases, but in most cases, there's not going to be any like just a variable is equal to something with a dx or dy, right? We're just going to say u is equal to x or u is equal to cosine 5x. But when we say dv is equal to something, that's going to include the dx. We're going to say dv is equal to x dx or dv is equal to cosine 5x dx. Does that make sense? So we need to identify what portion of this integral is the u and what portion of this is the dv. And so the u is just going to be one piece of this function, and then the dv is going to be the other piece of the function dx. Okay? So now, which portion do you choose to be the u and which portion do you choose to be the dv? Well, the general rule to use, and this works most of the time, is so the u, you're going to choose something to be the u, and then you're going to end up like, okay, what we're trying to do is, in this first step, is we're trying to get u, v, du, and dv. That's what we're trying to get, because when we have those four, we can make this whole formula, right? We need u, v, du. All right, but we're going to start with, we're going to identify what's going to be u and what's going to be dv. And so when we have u and dv, to get du, we're going to differentiate u. And then to get dv, we're going to integrate dv. And so with that, what you want to do is you want to choose the u to be whatever's going to result in the cleanest, simplest derivative. And then you want to choose the dv for that, so that whatever's going to be the easiest, cleanest integral. All right, so a good example of that is if you ever have the natural log of x as one portion, then it's going to be very rare that you'll ever choose the natural log portion to be the dv. You'll choose it to be the u, because when you take the derivative of natural log of x, it just goes to 1 over x. As opposed to the integral, it's like a complicated integral. All right, so when I look at this, cosine of 5x, that's easy to differentiate. It's also easy to integrate. When I look at x, I mean, this isn't hard to integrate, but when you differentiate it, it goes to 1. So in that case, let's go ahead and say that u is equal to x, and now dv is going to be equal to cosine 5x dx. Okay, now another reason to remember that the dv is going to have to include a dx on the end is because if we're going to integrate both sides to get the v, then if there's no dx here, we talked about this in the, I think it was the previous video or 2 videos ago when we went over the, is dy over dx a ratio? Is dy and dx a number? Do you treat them as numbers in integration? You can't, if there was no dx here, I can't integrate this. I can't say this doesn't mean anything. This isn't proper notation. Technically, we don't know what this means. Technically, until according to the technical math notation, this means nothing, but this means find the antiderivative. Okay, so okay, we have u and dv. Now we want to get v and du. So here's how we're going to get v. So the integral of dv is just v. What is the integral of cosine 5x? Okay, well, the derivative of sine 5x is cosine, it's 5 cosine 5x. So then if we do 1/5 sine 5x, then that would be the integral, because the derivative of sine 5x is 5 cosine 5x. 5 times 1/5 is 1. Now, you might say, well, what about the plus c? Yes, technically this is the antiderivative with the plus c, but with integration by parts, you don't worry about the plus c at this stage. If we carried that plus c with us through the process, it would just get absorbed into the final plus c. Okay, now, all right, we've got u, dv, v. Now we need du. How do we get du? We take this derivative. Du dx is equal to 1, so du is equal to dx. So now we've got everything we need to make to write all this out. So our original integral, x cosine 5x dx, according to this formula, is equal to what? It's equal to u times v, so 1/5 x sine 5x minus the integral of v du. So here's v, and du is just equal to dx. So 1/5 sine 5x dx. And there we go. See? This is a simpler integral than what we started with. What is this integral? So we can factor out a 1/5, and we get x sine 5x minus the integral of sine 5x dx. This integral here is minus 1/5 cosine 5x. Because the derivative of cosine 5x is minus 5 sine 5x. And so there we go. So we've got this integral is equal to 1/5 x. Let me put a different 1/5 x sine 5x plus 1/5 cosine 5x. And so let me bring the, let me distribute the 1/5. 1/5 x sine 5x plus 1/25 cosine 5x. Okay? But now, okay, so this is the capital F of x, so we want to put the plus c on the end. Now, this is the capital F of x. So the derivative of this is going to give you the original function. The derivative, if you take this derivative, you're going to get the original function. But now to make it the full antiderivative, you put the plus c on the end. So we've got 1/5 x sine 5x plus 1/25 cosine 5x plus c. Okay. Same process. We need to identify which portion of this is going to be the u and which portion is going to be the dv. And so when it comes to e, e to whatever power, that's just as easy to differentiate as it is to integrate. Okay, so what about t? Well, to me, it's nice that this goes to 1 if you differentiate it. So let's say that u is equal to t, and then dv is equal to e to the minus 3t dt. So you see with the u and dv, we've completely, we could make this substitution here. With everything gets substituted, we end up with what? U dv, right? Okay, so du dt is equal to 1, so du is equal to dt. And remember, the idea is that what we talked about is we're operating with like dt here like it's a differential. So I talked about this in detail it's like the previous video 2 videos ago when we're talking about is dy dx a number, is this a number? So go check that out. So we're not saying these are differentials. We're operating with them as if we're operating with these infinitesimals as if they were differentials. So, all right. Now here we can integrate both sides. This is proper integral notation. So we've got v is equal to, so we'll probably need a minus 1/3 and then e to the minus 3t. Now if you take this derivative, you get e to the minus 3t times minus 3. Yeah, so there we go. So t e to the minus 3t dt is equal to this. uv minus 1/3 t e to the minus 3t minus the integral of v du. So the integral of v du, which is dt. Right, we're going to have some sort of dt here, or else this is not going to be an integral. And it comes from the du is dt. Okay, so we've got minus 1/3 t e to the minus 3t. We could take out that minus 1/3. Okay, did integration by parts work? Well, the idea is this integral simpler than the original integral? Or if it's not, is this integral solvable? Well, this is simpler. We can solve this. So we've got minus 1/3 t e to the minus 3t. And then this is the same integral as here. And so it's minus 1/3 e to the minus 3t. So this is going to be minus 1/9 e to the minus 3t. And, okay, that's the capital F of t, meaning, so remember what we mean by that. This is like the general function for any derivative is this, okay? And this is equal to, in general, it's capital F of x plus c. This capital F of x, it doesn't have to be just one term. It could be multiple terms, like multiple different terms added together, like a full expression. The only thing is every single term, though, even if there's multiple terms, is going to have at least like one variable in it, one of the x's in it. There's not going to be any constants, just pure constants in here. And so the thing is, this capital F of x, just by itself, f prime of x is equal to f of x, right? This is an antiderivative of f of x. But the thing is, to make this the most general answer, all you got to do is add an arbitrary constant to the back end of the capital F of x. So this is capital F of t. So now all we need to do is do that. And there's the derivative, or the integral, the antiderivative. Okay. What's going to be the u and what's going to be the dv? Okay, well, cosine is easy to differentiate and to integrate. And I would rather take this derivative. So let's, as far as simplicity. But like, okay, you might do it this way where you see what's simpler to integrate and differentiate, and maybe it doesn't work. Well, you could still go back and do the opposite way. I mean, this wouldn't be that bad of an integral, right? 1/3 x cubed plus x squared. That's not too bad. So, but okay, we'll do u is equal to x squared plus 2x. dv is equal to cosine x dx. So du dx is equal to 2x plus 2. du is equal to, we'll do 2 times x plus 1 dx. Okay, here, integrate both sides. V is equal to sine of x. So x squared plus 2x cosine x dx is equal to u times v minus the integral of v du. V du. So 2 sine of x times x plus 1 dx. Okay, have we gotten a simpler integral? Yeah, it looks like we have. We might, I don't know how we're going to solve this yet, but this looks simpler. We still got a trig function here, sine of x, but now instead of a second order polynomial, we've got a first order polynomial. And so it looks like we'll need to, let's do integration by parts again. Okay, so we want to get, we're doing the, well, we can do this. Let's take that 2 out. So we want to get the integral of sine x times x plus 1 dx. All right, so u is equal to x plus 1, dv is equal to sine x dx, du is just going to be equal to dx, v is minus cosine x, right? du dx is the derivative of x plus 1 is just 1, so du dx is equal to 1, multiply both sides by dx. Here, the derivative of cosine of x is minus sine x. So the derivative of minus cosine x is sine x. So, okay. uv minus cosine x, x plus 1, minus the integral of v du. The integral of minus cosine x dx. So I'll put a plus here. Okay, so now, yeah, we can solve this. So minus cosine x, x plus 1 and this is going to be plus sine x. And again, we don't need to bring in c constants yet. Okay, so coming back here, we've got this is x squared plus 2x sine x minus, and then we brought the 2 out, and then minus cosine x times x plus 1 plus sine x. Okay, so x squared plus 2x sine x plus 2, let's just do 2x plus 2 cosine x minus 2 sine x. All right, so that's capital F of x, and we just put plus c. And that's it. Okay, so, remember, we're going to use integration by parts no matter what. And, I'm not even sure if we could, the table of integrals would give us anything. I don't see anything, so. Okay, well, what's going to be the, we could just make dv equal to dx and make u equal to inverse cosine of x. That's fine. And actually, we're going to have to do that because it wouldn't make sense the other way. If we made, how can we make this dv? Because we don't even know what the integral is. That's what we're trying to solve for. So, yeah, I mean, we know we have derivative rules for inverse trig functions. So, okay, we'll make du equal to inverse cosine of x, and then dv is just equal to dx. So, v is equal to x, du dx is equal to, let's check out the derivative rules for inverse trig functions. Okay, so derivative of inverse cosine is minus 1 over the square root of 1 minus x squared. Okay, so the integral inverse cosine x dx is equal to u times, oh wait, so yeah, this would be then if we multiply both sides by dx, we've got this, and then this is, why do I call this du? This is u. This is u, yeah, there we go, okay. U times v is x inverse cosine x minus the integral of v du. So we can take that minus sign out, and then you got 1 okay. And so, yeah, here's a good example. This looks more complicated than the original integral, but it's, it's really not about how complicated, but can you solve it? And if we look here, we can solve this. We can make a u substitution. We could say u is equal to 1 minus x squared. So du is equal to minus 2x dx. And therefore, minus 1/2 du is equal to x dx. So the integral if we make the substitution, we've got 1 over the square root of u times x dx is minus 1/2 du. So this is minus 1/2 integral of u to the minus 1/2 du. Minus 1/2, u to the minus 1/2 plus 1/2 is u to the 1/2 over 1/2. So this is minus root u. This is minus root 1 minus x squared. Okay, so what we've got is this is equal to x inverse cosine of x minus, there we go. There's the capital F of x, so now I'll just put plus c. Pretty cool, right? That's this integral. So here, I mean, when I see natural log, to me, we want to make that to where we're taking that derivative. You take that derivative, you get 1 over t, you get rid of the natural log, but we saw an example problem in the textbook on how to get this integral. You find this integral with you can use the integration by parts, just like we did in the previous problem. Yeah, you do dv is equal to dx, and then u is equal to natural log of x, and you go through the same process, and you can get the integral of natural log of x. And it's not that bad, but you know, if you tried it this way with u is equal to natural log of t, taking this derivative, and it didn't work, you could go the other way. But you know, this is definitely simpler. So, well, we're going to be taking the integral of this, but still, that's not too bad. So, okay, dv. Let's see what happens. We could always come back and try the other way if we need. dv is equal to t to the 4th dt. So du dt is equal to 1 over t. du is equal to 1 over t dt. Okay, in the power rule for integration says that we do 1/5 t to the 5th. That's not so bad. All right, so uv minus the integral of v du. So that's 1/5 t to the 5th times 1 over t. That's going to be 1/5 t to the 4th. So let's take out the 1/5. Yeah, and it's okay. So we could definitely integrate that. That's no problem. So this is minus, so this is, yeah, it's the same integral, t 1/5 t to the 5th. So 1 over 25 t to the 5th. And there you go. There's capital F of t, put the plus c. Okay, so when I think of I think it's the derivative of tangent x is cosecant squared. Is that right? So or it's, oh no, it's secant squared of x. Derivative of tangent x is secant squared of x. Okay. So what about the table of integrals? Okay, we have cosecant squared is minus cotangent. And so we could have, you know, instead of referencing the table of integrals, what we could have done is, so just taking a look at the derivatives of trig functions, the derivative rules for trig functions, and we would have seen that we've got this cosecant squared here. You know, and all we're trying to do is just see, you know, this is the part that seems that's going to be the issue. You know, how is what would be the derivative of cosecant squared? Like, we would use the chain rule to get this derivative. We would say, what is the derivative of cosecant? So no, it would be, yeah, you'd say it would be the derivative of cosecant squared of t would be 2 cosecant t times the derivative of cosecant t. It would be 2 cosecant t times minus cosecant t cotangent t, which is complicated, but we could still set up the integration by parts formula and see what happened. Okay, but we see here, though, that the derivative of cotangent x is minus cosecant squared of x. So what does that mean? That means that if the integral of cosecant squared x is minus cotangent x. Why? Because what is the derivative of minus cotangent x? You can bring the minus sign out front. It's cosecant squared x. So what we want to do is we want to say that dv is equal to cosecant squared t dt. And then u is equal to t. You know, it's whatever's going to be easiest to work with this, because that's the part that can mess us up. Like, what I mean is, like, t, yeah, you want to take its derivative, but you can take its integral, no problem. All right, so when you take this integral, you get minus cotangent t. Okay, and then du dt is equal to 1, so du is equal to dt. So the integral of t cosecant squared t dt is equal to u times v minus t cotangent t minus the integral of v du. So we take out that minus, and you've got cotangent t dt. Okay, so we could reference our table of integrals here to do this, but let's take a look at the derivatives of trig functions. Well, actually, okay, it might be a little more involved than I thought to figure out what this integral is. And so I'm assuming that this is going to be in the table of integrals that the textbook gives us. And yeah, it is. Natural log of the absolute value of sine x. So let's just go ahead and use that. Okay, so plus natural log of the absolute value of sine t plus c. Okay, let's say that u is equal to the natural log of x squared and dv is equal to dx. You know, because I feel like taking this integral would be a mess. So du dx is equal to 2 natural log of x times 1 over x. So 2 natural log of x over x. So du is equal to 2 natural log of x over x dx. And then v is equal to x. Right, integrate both sides here. So the integral of natural log of x squared dx is equal to uv x natural log of x squared minus the integral of v du, which is just going to be 2 natural log of x. Bring the 2 out. Okay, now we just did the integral of natural log of x a few problems ago. Or no, we did inverse cosine of x. Okay, so I guess it probably wants us to just, we could reference this in the textbook, but this is not in the table of integrals that it gives us. So yeah, I mean, this is a simpler integral than what we started with. And we can do this the same way we did inverse cosine, we can do here. So u is equal to natural log of x, dv is equal to dx. So v is equal to x, du is equal to 1 over x dx. So is equal to uv minus the integral of v du is just dx. Okay, so this is okay, so we can write this And wait, this will be plus. Okay, there's capital F of x. Just add the plus c. Okay, we'll do the rest of the problems in the next video.